Sorry, guys. Sorry, guys. Karina, you in here? Open your mic,
Yes,
Karina. All right. I am sorry. What happened is I get into this thing and it has a new program it wants to upload. So I apologize for that.
It's okay.
Guys, if I do something silly like end the class early, tell me, Mr. Popovich, it's only 10:10. You have 45 minutes to go or something, all right? Please do that because this is for your benefit, not mine, all right? Okay, so we got to get going here. And I got to find the show all windows. Can you see this? Can you see the slideshow? Guys?
Yes.
Okay. So we got to get on the ground running. I am probably going to extend one of the meetings next week to try and catch up to the other class, okay? So you can attend or not. I mean, these are it's your free will. Okay, this is basically what we're going to cover in chapter 1, the metric system, units of measuring, estimated digits, measuring, sig figs, scientific notation, chem and physical properties and changes, dimensional analysis, temperature conversions, density, and the classification of matter. Now, have you all had, do these topics make sense to you? Are these topics ones that you have covered before?
Yes.
And keep in mind, I know what the curriculum for Intro to Chem is. Is there anybody that has something on this list that they haven't covered before? I'm hearing crickets. Crickets are good because crickets mean I can go through this stuff really fast. All right, the fundamental units. If we're dealing with a mass, we're dealing with kilogram, length meter, time, second, temperature Kelvin, electric currents an ampere, and the amount of substance is a mole. This has been determined by scientists chemists throughout the world that these are going to be the standard units. Now, most of the world, does anybody remember Jimmy Carter? Or no, you don't remember Jimmy Carter. You weren't alive then. Do you know who Jimmy Carter is? No? Jimmy Carter, President of the United States, wonderful man, a sweet man, a very, very sweet man who should not have been president. Jimmy Carter tried to drag America into the metric system around 1970 or 1970, I'm going to go about 76, 77. You can tell how far he got because when you go to buy your meat, do you buy it in kilograms or pounds? Everywhere else in the world, you buy it in kilograms. You put gas in, you don't put it in gallons, you put it in liters. Now, there are prefixes within the metric system. Use this mnemonic. King Henry died Monday drinking chocolate milk. And we're going to use the Monday to be meter, which is the original measure. Okay? King stands for kilo. It's 1,000 times larger than the original basic measurement. Hecta, or Henry, stands for hecta, 100 times larger than the original measure. Deca, 10 times larger. If we go into a deci, that's 1/10 of the original measure. A centi or chocolate is 1/100th, and milk, milli, is 1/1000th of the original measure. Think of it like a staircase, guys. you have 7 steps to the staircase. Now, Karina, you there?
Yeah.
Is a kilo bigger or smaller than a milli?
Bigger.
So if a kilo is bigger than a milli, do you need more millis than kilos to have the same number?
Yes.
Perfectly fine. So as we go down each step, we are going to multiply by 100. If I have kilos and I want hectos, I have to multiply the number of kilos I have by 10 to get the hectos. So every time you go down a step, that means I am multiplying by 10. Ian, you out there, Ian? Ian? How about Gabe? Gabe, you out there?
I'm here.
Okay, Gabe, if I have 2 kilos, how many decis do I have? How many steps are you going down, Gabe? Count them with me. 1,
Right.
2,
2,
3, 4. So each step I have to multiply by 10. I go down the first step, 2 goes to 20. 2 kilos is 20 hectares. I go down the next step, 20 hectares is 200 decas. If I go down the next step, 200 decas is 2,000, whatever the label is, if it's meters, liters, or grams. If I go down one more step, that 2,000 goes to 20,000 decis. Every step I go down, I multiply by 10. On the other hand, Gavin, you're out there. Gavin?
Affirmative.
Okay, are millis bigger or smaller than kilos?
Smaller.
So, are there more millis or a kilo?
There's more millis in a kilo.
So each time when we go in this direction, when we go up the steps, each step that we make, we're going to divide by 10 for each step. So Gavin, if I have 64 centis, how many hectares do I have? 64 goes to the deci. When I pause, Gavin, this means you're supposed to answer. 64 goes to?
640.
No, we're going up the staircase. We're dividing.
Or sorry, my bad.
This goes up?
It's gonna be 6.4.
6.4?
And 0.64. 0.064 and 0.0064.
Okay.
Hectares.
Are you guys kind of understanding this? Basically, it should be review and it should be having everything. Now, each measurement you do has 3 different parts to it. The first is the number part. That gives you an idea of where it lies within the second part, which is the unit. The third part is the error estimation. So the number gives you a comparison, the unit gives you the scale, and the error estimate is implied at plus or minus 1 in the last place. So if I have 642 centimeters, that means I have a range. My accuracy of my measurement is only good enough so that I know that it lies somewhere between 641 and 643 centimeters, because the 2 is an estimated digit. Am I saying anything you don't know? Stop me, slow me down if need be, guys. Now, if you're looking at the number itself, the last number to the right, is always the estimated number, except when we're dealing with exact numbers. And an exact number is a counted unit or an exact conversion, like if you have 7 days in a week. Like if you had, there are 4 quarts in a gallon. There are exactly 4 quarts. So that means there are 4.000000 all the way out to infinity quarts in a gallon. Estimated digit, Karina, number 1.
The last 4.
Last 4. Ian, you out there, Ian? Ian doesn't want to play, or is connecting to audio somehow.
Yeah, I think he hasn't selected his audio.
No problem.
Choice.
Gavin, next one, 12.5.
The 0.5 is the estimated number.
Okay. Who thinks they're good at this? 630 pencils.
It would be the 3.
Everybody buy that? How do you get 630 pencils? What do you have to do to get 630 pencils? Don't you have to count them? Don't you have to count this to ensure you have 630 pencils? It's exactly 630 pencils, right? So there is no estimated number in an exact number. We good with that? Okay. Let's look at this. Karina, is there an estimated number in this way, in this mass?
Is it the 4?
Absolutely. Guys, just because it appears in lights does not mean that it is not, that last digit is not estimated. The balance itself has taken it upon itself to say, okay, I'm going to say that that was a 4. That number is a 4. The balance itself estimates it. So even though it's in lights, that 4 is an estimated number. Now, you have to be able to determine the known numbers and the one that you estimate. All right? The way you do that, you take the smallest numbers that are marked on your instrument, and you choose 2 of the lines that are marked, and you subtract them. So in this case, I'm going to subtract 60 and 50. That gives me 10. Now, the second thing you got to do is you got to count the spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I take the difference that I have from the markings, the 60 minus 50, 10. I divide it by the number of spaces, 10. So that gives me the value of what the line is. Okay? So in this case, I got 10 divided by 10. Each one of these lines is worth a milliliter. Now I got to estimate how far it is between these. Would you agree that my liquid, if I'm looking at it going up, would you agree that my liquid is 51, 52, not quite the 53, because I'm looking at the dark line there? Would you all agree with that? It's somewhere between 52 and 53. All right, so I'm going to start. It's between 52 and 53, so the 2 is an exact number. Now what I have to do when I'm measuring is I have to go one more decimal place to the right. It's somewhere between 52 and 53. How far would you say that's up there, Gabriel?
0.9.
0.9. Perfect. So the way I'm reading this measurement is I have 52 and it's about 9/10 of the way up. So I'm reading that as 52.9. Are we good, guys? Are we good with this? Questions on this? Ladies and gentlemen, this is true in a fact. I take more points off for measurement readings and significant figures than I do anything else. If you didn't learn it in intro, learn it now, because you're not only going to get penalized this semester, if you go on to Chem 2, you're going to get penalized there. More in the lab than in the lecture. but you will get penalized. So learn it. All right, got to flip in. Any questions about measurement readings? Significant figures. All non-zero digits are significant. So anything 1, 2, 3, 4, 5, 6, 7, 8, 9, that is definitely significant. It's the zeros we have to worry about. If the zeros are captive, if they are between 2 digits, they are significant. So 904 has 3 significant figures. 1005 has 4 significant figures. If you have a leading zero, by definition, a leading zero is a zero to the left of the first digit. If you have a leading zero, it is not significant. So if I have 0.00345, that has 3 significant figures. Basically, they placehold. They give you an idea of how big or small your number is. Now, all this is straightforward. The choice comes when we have trailing zeros. Trailing zeros are any zeros to the right of the last non-zero digit. It's only significant if there is a decimal point in a number. So if I have 0.0009320, the 4 zeros to the left of the 9 are not significant, but the 0 to the right of the 2 is. If I have 34,500, I have trailing zeros, but no decimal point. So this means that the 3, the 4, and the 5 are significant. The 2 zeros are not. All right, we're going to be simple about our rounding rules in this class. If you have to round something because of a calculation and a determination of the fact that you have to have a certain amount of significant figures. If you are rounding, what we're going to do is we're going to look at the digit to the last digit that we can report out. The last digit we can report out, we figure out how many significant figures we can have, and we start from the left, and each place counts 1. So if I have 3 significant figures for this number, I'm starting to the left. The 862 are the numbers I'm going to report out. I got to look at the place just to the right of the last significant figure I can report out. If that number is less than 5, the last significant figure doesn't change. If it's 5 or more, the number rounds up. So if this were 0.0862552, I would have to report that out as 0.0862. By the way, this number should be reported out as, if I'm reporting out 3 significant figures, it should be reported out as 0.0862. Questions? Okay. Now, rules. You round when I'm doing addition and subtraction. I round to the same number of significant figures as the least accurate number. By the least accurate number, I mean you look at the number and you determine how far that number goes to the right. If I'm adding 35,000 and I am adding 4,100, the 35,000 is only accurate to the thousands place. The 4,100 is accurate to the hundreds place. So if I'm adding those two numbers out, I have, my answer is going to have the same number of significant figures as my least accurate number. 35,000 plus 4,100 equals 39,000. If I add 16.02 and 14.321, The 16.02 only goes 2 places past the decimal. The 14.321 goes 3 places. So therefore, my answer can only go 2 places past the decimal. I add these two numbers together and I get 30.341. 30.341, I can only report it out to 2 places past the decimal. So that gets reported out as 30.34. Questions, guys? All right, how many significant figures should my answer have? Gabe?
3.
3. Gavin, the second one, how many significant figures should that have?
3.
Okay, Karina, how many significant figures should that have?
1.
So if I subtract 1.2 from 40,000, my answer is 40,000. Because basically, the 1.2 is insignificant when compared to 40,000. It's like spitting in the ocean. Does your spit really damage the ocean any? Because it's diluted by a mass so much bigger. Okay? I subtract 102 and 106. How many significant figures should my answer have? Anybody?
It should have 3.
I do 102 minus 1.6. I get 100.4. Since the 102 only goes out to the units place, I have to report my answer as 100 with a decimal place. Or I can use scientific notation. Now, Gavin, you have your calculator with you.
Yes.
All right, add 996.32 and 5.895.
All right. Want me to give the answer or?
Give me the rough answer.
1002.215.
Okay. What are you going to, what's your answer? How far does your answer go to the right of the decimal place?
To the 1,000th or 100th place. Sorry.
Hundredths place. So if you report it out 1002.215, the 1 is the last significant figure you can report out, correct, Gavin?
Yes.
So I look just to the right of the 1, I get a 5. Am I rounding that up or not?
Rounding up to 2.
So I have 1002.22.
Yes.
Wait a second. Is that right?
That should be right.
Okay, Gavin. I have 5 significant figures, right?
Yeah.
And I'm adding 4 significant figures, but the answer you gave me has 6 significant figures. Is that right?
Yes.
Good. Absolutely fantastic. Because you can gain significant figures when you add. You can lose significant figures when you subtract. Does that make sense to you? For example, if I subtracted 102 minus 2.6, my overall answer should be 99.4, correct? But I can only report my final answer to the units place. So even though I started off with 3 significant figures, I lost 1. Do we need to go through the, I just went through it. The key here, note, you can add or subtract something and the number remains the same. And the other note, you can lose significant figures if you subtract, you can gain them if you add. Now, I think this is the easier one. In multiplication and division, you round to the same significant figure as your factor with the fewest significant figures. So if I multiply 32 and 16.1, 32 has 2 significant figures, 16.1 has 3. So therefore, my answer is going to have 2 significant figures. So first answer, Karina. How many sig figs?
2 significant figures.
Gabriel, second one.
4 significant figures.
Okay, third one. Anybody?
2, actually.
It should have 3 significant figures.
Gabe, when you add the 3.1 and the 23.45, that gives you an answer of 26.6, right?
Oh, right. And then
So that has 3 sig figs times 3 sig figs. Your final answer should have 3. Now, guys, when you are doing an operation, you always do what's in the parentheses first. Now, by those silly rules of math, when you do multiplication and addition, what you do by the rules, you multiply first, then you add. So if you do the multiplication of this bottom one, multiply 5 by 3.68, you're going to get an answer around 18, which has to be rounded to 20 because it has 1 significant figure. Okay? Now, if I'm taking 20 and adding 4 to it, my final answer is going to be 24. Now, this is going to become important when you're actually doing work in the lab, or especially when you're converting mass of something into moles of something. What you have to do when you are choosing a conversion factor, you have to choose a conversion factor such that you do not limit the sig figs because of the conversion factor. If I'm choosing my conversion factor, I'm trying to convert quarts to liters, and I have my 3.251 quarts, that has 4 significant figures. So my answer should have 4 significant figures. So if I'm looking at these, which one am I going to choose, Gabe?
0.9464.
I can choose that one. I could choose the bottom two because that has more significant figures. I can choose a conversion factor that is more accurate. I can't choose one that is less accurate. So I can't choose 0.95 or 0.946. Are we good with that? You have 54.60 grams of methane. Karina, which conversions do you use?
The bottom 2.
Bottom 2 would work. Okay, quickly on scientific notation. And guys, you are going to be very, very happy, especially when you get to Chem 2, because Chem 2 is going to work with very, very large numbers and very, very small numbers. Any number can be represented as a product of a number between 1 and 10 and the power of 10. So what this means is when you are looking at a number, you move the decimal place such that you only have one integer to the left of the decimal. Then the power of 10 is going to depend upon the number of places you moved it and in which direction. If the decimal is moved to the left, the power of 10 is positive. If it's moved to the right, the power of 10 is negative. So if I have 345, I want one digit to the left of the decimal, 3.45. I moved the decimal. I moved it from here. I moved it to the left 2 places. If it's to the left, it's positive. So my 3.45 gets multiplied by 10 squared. If the decimals move to the right, the power of 10 is negative. So if I have a number, 0.0671, I move the decimal such that there is only one integer to the left of the decimal. I've moved it 2 places, but I've moved this one to the right. So when I multiply it by 10 to the power, that number is -2. Engineers use a different system. And actually engineering they're smarter. So you can represent 10 to the 12th power by saying E12. You can use the same notation. Times 10 to the -3 is equal to E minus 3. Questions on that? Not even a little chuckle from any of you? You don't laugh, I'm not going to include these slides then. Understand this. If you don't know significant figures, then you lost at least 250 points because of significant figures between lecture and lab. Try to keep the points lost to a minimum by learning the rules. I made up the 250. Are we good? Any questions on measuring, scientific notation, sig figs? Are we good with that? I have to change to another slideshow. So I got to stop share. Got to go to change screen and is everybody seeing the thing, chemical and physical properties and changes? Are you seeing this?
Affirmative.
It's one of the hardest concepts to get your mind around because when we are testing you in lecture, we're testing your knowledge of English more than anything else. It's how the problem is presented. It's how the problem is presented that tells you whether it's a change or a property. When you have a change, something has occurred. When you have a property, nothing has occurred yet. It just has the possibility of occurring. Does that kind of make sense to you? You'll learn what physical, chemical properties, and you'll learn how to distinguish physical changes from chemical changes. That's all we're doing in this particular slideshow. Property is nothing more than a trait or an attribute, characteristic. Thus, basically, when we're talking about a physical property, we're talking about the characteristic of that substance. If we're dealing with a chemical property, it is the ability to transform into another substance. It hasn't occurred yet. It just could occur. If we have water, we can change water into its elements, hydrogen and oxygen. So the chemical property of water is such that if I add an electrical current to water, it can change to hydrogen and oxygen. A physical property would be doing something that does not alter water from being water. If I boil water, I don't change water. If I boil water and I put a glass over top of it, the water will condense on the glass and it looks just the same as the water I was boiling. So we're talking physical properties. We're talking about the quality of a substance. It's a property that can be measured or observed without changing the composition. Basically, we're talking odor, color, volume, physical state, solubility, density, melting, and boiling point. Guys, physical properties are what we use in chemistry to determine what a substance is. All densities are unique. The density of water is 1 gram per cubic centimeter, which is different than the density of copper, which is 8.63 grams per cubic centimeter. Copper is different from aluminum, which is 2.7. You can use a physical property to help identify what a substance is. Basically, how do we detect physical properties? Anybody? I got to see
Using our
my
senses.
participants. Okay, I'm sorry guys, I've only got 5 of you to ask questions of. What are we talking about? You detect physical properties by seeing, hearing, come on, touching, smelling, taste. Not so much taste in chemistry, guys, but you do. You do use taste. Has anybody bitten into a lemon? If you've bitten into a lemon and I tell you acids taste sour, what is your conclusion about lemons?
A lemon is an acid.
A lemon contains acid. So yes, this is the way, this is how you detect physical properties. We use our senses. So those are the typical physical properties. When we're talking about a chemical property, we're talking about its reactivity. Basically, we're forming a new substance from an old substance. So if we're changing substances, what do you think happens to the physical properties?
They can possibly change depending on the reaction.
To a large extent, that's how we detect if something reacts or not. We look at the physical properties beforehand and the physical properties afterwards. If we detect that there is a change, then you probably do have a chemical reaction. For example, do you remember doing the experiment last in intro where you didn't do experiments, did you? Okay, let's do this one. Has anybody ever seen iron? Straight iron? Nobody? Steel.
Not pure iron, but yeah.
Steel. Have you seen steel? What's the color of
Yes.
steel, Gabe? Steel, what's the color?
Isn't it like silver?
Silvery, okay.
Yeah.
What's rust look like?
No, what? Sorry, you're cutting
What
out.
is
What'd you say?
rust?
Rust
What
is
does
like
rust look like?
a almost reddish, bronzish kind of thing.
Okay.
Right?
Is rust, I mean, does it flake off? Can you
Yes.
take it and crush it?
No.
You can't crush rust?
Oh, no, you can.
What about steel?
No.
So this is what I'm talking about. You're using a change in the physical properties to detect a chemical reaction has taken place. So when we're dealing with the chemical property, that is the possibility of transforming something into a new substance. Yeah, I think it's just a repeat. It's stuff I've already said. Guys, you ought to be happy I don't just sit and read from these things. All right. If I am dealing with a physical change, the substance has been altered either in its form or state, but not its chemical composition. If I just went through and had my house painted, different color. I've changed it, but the wall is still the wall it was before. That drywall is still the same. It's that gypsum compound. That's not changing, but I've changed its appearance. Okay? If I change state, if I heat a substance up and water goes in, it steams up, and then I put a glass on top of it, it's going to condense back. The water hasn't changed. If I sublime iodine, I have these nice purple crystals. I heat it up. The iodine makes this nice purple cloud. And then if I have a dish over top of it with ice in it, that iodine will crystallize back. It's not changing. So basically, if I change the way it looks, I take a piece of paper. Let me take a useless piece of paper. I have a piece of paper. Is it different in size and shape? But is this paper molecule the same as this paper molecule? Have I changed that at all? That's a physical change. I can crunch it up. I can take a piece of paper and fold it. I'm not doing anything to change the paper. Now, if I take this piece of paper and I put a match to it, have I changed the molecules of the paper? I've changed this cellulose into carbon dioxide and water. I physically, I'm sorry, excuse me, scratch that physically. I have chemically changed the molecules from one thing into something else. Again, you know a chemical change has occurred if the physical properties have changed. So a physical change is a change in the appearance, size, but it is not a change of the chemical itself. A chemical change involves a change of the atom or compound into another atom or compound. Okay, this stuff is not. All right, now we're going to get into some problems. Elemental bromine is a dense, dark red, pungent smelling liquid. Are those first of all, is anything changing? Nothing's changing. So are they physical or chemical properties? Am I implying that bromine can do anything? So what does this have to be? Come on.
Physical.
Physical what?
Properties.
Physical property. On the other hand, elemental bromine will react vigorously with elemental sodium metal to form a white solid. Is this characteristic of a physical or chemical property? All right. Let's ask the question first. Read elemental bromine will, the important word in this sentence, will react. Has it occurred yet? So is it a property or a change?
It's a property.
Property. Now, am I implying that it can change into different things? Are the properties of the results Are the properties of the results different than the properties of bromine to begin with?
Yes.
So therefore, if it's different properties, this is a chemical property of bromine. Are we good with that?
Yes.
Oven cleaners contain sodium hydroxide, which converts the grease oil splatters to a water-soluble material, which can be washed away. Has it occurred yet?
No.
So if it has not occurred, is it a change or a property?
Property.
Property. Now, do I imply that the properties are different beginning or end? Is grease water soluble? Those of you that have tried to clean out ovens and you go and do it with just water, can you clean it? Can you clean grease off with water?
I don't believe so.
No, no,
attempted
you
it.
can't. Take it from me, who's tried to do it many occasions. What you have to do is you have to do something to the grease and oil to make it water soluble so that you can get rid of the grease. So is this a chemical or a physical property? Are we implying the change will occur? So we have a chemical property. A rubber band stretches when you pull on it. Has it happened yet?
Yes. No.
When you pull on it. Again, we're talking semantics here. It doesn't specifically say, I pulled on a rubber band and it stretched. You understand the semantic difference here? So it hasn't occurred yet. Is it a property or a change?
Property.
Okay. Now, does the rubber band, after you let go of the rubber band, is the rubber band the same as it when it started?
Yes.
Yeah.
So is it a physical property or is it a chemical property?
Physical.
You got iron pan rusting in a sink. Is something changing?
Yes.
So is it a change or a property?
To change.
Okay. By rusting, are we changing the property?
Yes.
So is it a chemical or physical?
Chemical.
Last one, hydrochloric acid has a pungent odor. Physical,
Physical.
chemical property or change?
Property. Physical.
Physical property. Okay, hydrochloric acid will burn a hole. Jesus. Did I spell hole that way? Okay, wait.
Well, maybe it's a whole hole.
Yeah. I don't need this. I need to end the show. I got to change this. This offends me. Thank you. Hydrochloric acid will burn a hole in your jeans. Property or change? Has it
Change.
happened?
No.
So is that a property or a change?
Property.
Oh,
Property. Chemical or physical?
Chemical.
Chemical. Copper compounds have a blue color.
It's property.
What kind? Physical or chemical?
Physical.
Physical. Copper metal combined with oxygen to give a green color. Think of the Statue of Liberty.
That's a chemical change.
Chemical change. Because copper is normally brown, copper oxide is green. So it has already happened. That was a chemical change. Are we good with these guys? you kind of understand what's going on with chemical and physical changes in properties now? We good? Are we good, guys?
Yes.
Affirmative.
Okay, now. Okay, now I got to get into and show. Share screen. Are you seeing this? Are you seeing the slide now? Are you seeing the slide with
Yes.
temperature on it?
Yes.
Okay, I'm not going to use the F word. I will try not to use the F word. Depends upon how much you guys frustrate me. Fahrenheit, we do not use Fahrenheit. It is all metric in here. Centigrade, also called Celsius. If I say centigrade or I say Celsius, I mean the same thing. It's based on a scale of 100. And Kelvin is the best temperature because it relates the temperature to when the temperature is at absolute 0. Kelvin is the best temperature to use. So how do we convert one to the other? Kelvin's easy. If I have Celsius and I want Kelvin, I just add 273 or 273.15. Guys, most of the measurements in centigrade, most of the thermometers that are out there measure to the estimated digit of the tenths. So if you have a temperature that's out to the tenths, you got to add 273.15 or 273.2. Now, if I have Kelvin and I want Celsius, I just simply subtract 273 from it. If I have Fahrenheit and I want centigrade, I subtract 32 from the Fahrenheit and divide that by 1.8. If I have Celsius and I want Fahrenheit, I multiply 1.80 times the Celsius temperature and I add 32 to it. Good slide to remember, good formula slide. So what did we come up, how did they come up with the 1.8? Well, let's think about this. What's water freeze at Fahrenheit? What's the freezing point of water?
32 degrees Fahrenheit.
32 degrees. You may not know this, or you may. What's the boiling point? Hint, hint, hint.
212 degrees.
212 degrees. So if we're comparing Celsius with Fahrenheit, we first offset. We offset the number by 32. So if we have Celsius, we have to add the 32. Now, the amount of heat that it takes to raise the Fahrenheit scale from 32 to 212, or the amount of heat that it takes to raise the temperature 180 degrees, is equal to 100 degrees Celsius. So therefore, if I want to change the Fahrenheit scale into the Celsius scale, I have to multiply the Celsius by 1.8, or 180 degrees divided by 100. Does that make sense to you? Now, the difference in Celsius is the same as the difference in Kelvin. So if you have an equation in which you have to subtract one temperature from another, it doesn't matter whether you subtract the number in Celsius or Kelvin, because the number is, the amount of degrees are going to be the same. The way you get from Celsius to Kelvin is you add 273. You're going to add 273 to the higher number. You're going to add 273 to the lower number. So you're, in effect, subtracting the 273 out. So if you have an equation with a difference in temperatures, you can use Celsius. You do not have to convert it to Kelvin. Average human body temperature is 98.6. Express this in Celsius and Kelvin. My formula, 1.8 times my Celsius temperature is equal to, my 1.8 times the Celsius plus 32 is equal to temperature Fahrenheit. My T Fahrenheit is equal to my T Celsius is equal to my T Fahrenheit minus 32 divided by 1.2. I do this math out, I get 37.0. So if I use my conversion from Celsius to Kelvin, I have to add, not 273, I have to add 273.15. Fairly easy. If I give you a temperature on the test, would you be able to convert it? Questions? All right, we're going to get into density. Okay. Formula, the units for density are grams per cubic centimeter or mass per volume. You can have pounds per gallon. That is a density. You can have kilograms per quart. That is a density. Now, I like to explain this with something called the density triangle. And what you do for the density triangle is you put the mass on top and the density and the volume on the bottom. What that means is if you have the mass and the volume, there's a line between them. You divide them to get the density. If you have the mass and the density, there's a line between them. You divide them, you get the volume. This line doesn't exist. If you have the density and the volume, you multiply them to get the mass. You can do it that way, and you can also just simply take care of your labels. My mass is 35 grams, and it takes 7 cubic centimeters of space. Calculate the density. You're going to have 3 problems, guys. 3 problems in density. You're going to be given the mass and the volume, asked to determine the density. You're going to be given the density and the mass, asked to determine the volume, or you're going to be given the density and the volume and asked to determine the mass. Only 3 types of problems. In this one, since density is equal to mass divided by volume, I take my mass, 35 grams, divide it by 7, and look at my label. I divide grams by centimeters cubed. My label ends up being a volume. So therefore, the density is 5 grams per cubic centimeter. If I have the mass, if I want to find the mass and I have the density and the volume, look, the density is grams per milliliter. The volume is a milliliter. So if I multiply the grams per milliliter by the milliliters goes away and I'm left with grams. So if I can look at it at the labels, or I can look at it at the density triangle. The density triangle, we have the density, we have the volume. It says to multiply the 2 of them. So I take 1.52, multiply it by 25. I end up with 38 grams. Notice, 3 sig figs divided by 2 sig figs. My answer has 2 sig figs. If I have the volume, if I have the mass and I have the density, then to find the volume, I just divide the mass by the density. Okay, look, I have grams. The label for mass is in grams. Label for density is in grams per centimeter cubed. If I want to get rid of the grams and end up with the centimeters cubed, I have to basically multiply this by multiply the grams by the reciprocal of density. If I'm multiplying by the reciprocal, that means I'm dividing. So I set up the problem, 35 grams times 1 centimeter cubed divided by 1.2 grams. The grams cancels. I'm left with milliliters. My volume is 29 milliliters. Okay, ladies and gentlemen. Did that. Okay. Please do one of the problems. Karina, do one, the first problem. Gabe, 2. Gavin, 3. Layla, 1 again. And I think that's all the people that are here. Okay, final answers. What'd you come up for the first problem?
I got 1.2.
Layla?
I got that also.
Okay. I got it too. Problem number 2, Gabe.
All right, I don't think I got it, but I got 0.3.
No, it's not right. What you do for the, gotta get the slide back. What you do, you have to, because it's displacing, the original volume of the solid was, or of the liquid was 23.7. When you put the solid in, that increased to 26.8 by Archimedes' principle. The object will displace the same volume as it contains. So to get the volume of the metal, you subtract the 26.8 and the 23.7, and you end up with 3.1. That would be your volume. You then divide your 8.321 by the volume, and that gives you 2.7. Okay, Gavin, the third one.
1.02 milliliters.
Is that right? Yep, it is right. Sorry, I was looking for sig figs. Okay, guys, we're stopping there. Now, I had hoped to be through dimensional analysis and matter as well. Matter, I'm not concerned about because you've already had matter probably throughout high school. You guys know what that basically is. Review the PowerPoints. Review the PowerPoints for matter, dimensional analysis. Same thing. You have done this work before. Look I wouldn't go so much my PowerPoints for the dimensional analysis because I do something crazy for that. So I would not look at the PowerPoint. What I would do is I would look at a video, the video that's in the online outline, or go through and do the text. I'm sorry, guys, I have to go right now. Somebody just came in a few seconds ago. Yeah, somebody popped in a second ago, but I have to go because I got to get my dog to the vet by 10 o'clock. All right. This has been recorded, so it's available for you. Take care, guys. I will see you on Tuesday. I probably will extend the Tuesday time beyond the normal time to try and catch up with the other class. Okay?
All right, thank you.
Take
Thank
care,
you.
guys, and take care, and I will see you on Tuesday. I'm
right,
sorry,
thank
as I
you.
said, I do have to get out of here.